Assalamu alaikum. Hope you are doing fine. We have learned about electric flux. We know the number of electric field lines passing through a given area kept perpendicular is referred as electric flux. In this video, we are going to learn about Gauss Law, which plays a very important role to deduce the electric flux due to a charge or charge carrying object. To do so, I consider a sphere which encloses a charge. I consider this one as a positive charge which is enclosed by this sphere of radius r. Here the radius is r. We know very well where there is a charge, there will be an electric field around it. When I talk about the positive charge, it comprises of electric field lines projecting outward. In this manner, I take one such electric field line which is acting outwards because we have a positive charge here. So in this way, the direction of this electric field line is acting outwards, and it provides us the direction of electric field. It is known to us. Here, to find the electric flux, I take a small area, something like this. This area is kept perpendicular to this electrical field line. Now, if you look at this carefully, here a perpendicular line drawn to this area gives us the direction of this area element, that is a dA vector, and from the diagram the angle between electric field and the direction of area element is taken as theta, and it is nothing but 0 degree. So the angle between them is 0. So in this way, we know the expression for electric flux, which is written letter 5e, and it is nothing but closed integral of E vector dot dA vector. Here we have closed integral for the reason that the charge is surrounded by a closed surface. So we have a closed integral here. Then here we have a dot product. This can be written in this manner. Closed integral of, instead of this, we can write it this way: EdA cos theta. Okay, we know in case of dot product, we have A vector dot B vector, then this can be written as AB cos theta. We have followed the same method here. So in the place of E vector dot dA vector, we have written EdA cos theta. Now, already I told you here the value of theta is 0 degree. So this equation will become 5e. Now it will become close integral of E dA cos of 0 degree. Here cos of 0 is 1. So this equation becomes something like this. Cos integral of E dA. When I multiply this with 1, no change will occur. It remains this way. So the final equation that I get is nothing but 5E is equal to closed integral of E dA. I box this, then I go ahead. I can write this final equation in this manner. It's can be written as 5E equals to, now E is taken out, E closed integral of dA. Here, integral of dA, see, closed integral of dA. Here d stands for differentiation. If you integrate this term, we get a. Here this get cancelled. So in that way, here closed integral of dA is equal to A, and A stands for area. Area of this sphere. We know area of this sphere is nothing but 4 pi r square, and here we have E. E stands for electric field. Here E is obtained. E stands for electric field. E is obtained from Coulomb's law. What is that? Alright. To find E value, what I do? I start from Coulomb's law. What is that? Coulomb's law. Coulomb's law says that F equals to 1 upon 4 pi epsilon naught, then Q into small q upon r square. Okay, here Q is one charge of an object, small q is the charge of another object, and r is the distance between these two charges, and 1 upon 4 pi epsilon naught is a proportionality constant. This we have learned earlier. Now, how to get E from Coulomb's law? Let me tell you. We know E, electric field, is nothing but force upon charge. Force upon charge is nothing but electric field. Now I am going to substitute the value of F from here. So what do I get? Very carefully. Write the value of F. F is 1 by 4 pi epsilon naught, capital Q, small q upon r square. And here 1 upon q is written this way. So what I have done actually, written this equation E is equal to F upon Q as, this is written as 1 F into 1 upon Q. Okay, so in the place of F I have mentioned its value, and 1 by Q is written here as such. I hope you have understood. Then the similar terms get cancelled here. This to get cancelled, and what remain is nothing but E. Here E is equal to 1 upon 4 pi epsilon naught, capital Q upon R square. This is the electric field. I box this. Okay. I got the value of E, and we know the value of E. This two I am going to substitute here in this equation. So to make my work easy, I name this equation. This named as equation number 1, this is named as equation number 2, and this one is named as equation number 3. Now I am going to substituting 2 and 3 in equation number 1. If I do so, what I get? See, now right here 5e, the place of e I write this 1 upon 4 pi epsilon naught q upon r square. Then the place of e I write this 4 pi r square. Now 4 pi cancel, and here r and r square get cancelled, and what remain is nothing but this. When I get 5e equals to q upon epsilon naught. This is the final equation, and it is nothing but, what is this? It is Gauss Law. Gauss Law. Now using Gauss Law, one can get the electric flux due to a charge or a charged object. And here I make a little changes to this. What is that? Instead of writing it as Q, I write it as Q. See. So what for it stands NCL, I write. Here Q NCL means enclosed charge. What is this? Here charge is something but enclosed charge. The charge which is enclosed in the surface is alone taken here in a Gauss Law. So here the surface which encloses the charge is known as Gaussian surface. What do you call this? It is known as Gaussian surface. The Gaussian surface plays a very important role in a Gauss Law. It is not necessary for Gaussian surface to be spherical or of a particular shape. It can be of any shape. Now even you can take a random shaped Gaussian surface. I will show you. Suppose you have that I mentioned here. Suppose you have a charge here, plus charge. It is surrounded by a sphere. It's surrounded by a sphere. Okay. Then suppose there's one more surface is present around it. The arbitrary shaped surface. It do not have a perfect shape. Then I take one more surface here. This surface is also of arbitrary shape. Do not have a particular shape. Now, in these cases, suppose this is the electric field lines. Due to this positive charge. Here, if you look at this three surfaces, closed surfaces, you may find they have different surface area. I take the surface area of this sphere as A1 and the surface area of this arbitrary shaped surface as A2, and the area of this closed surface is taken as A3. Though they are entirely different, here A1 is lesser than A2 and A2 is lesser than A3. In simple words, I can say A3 is greater than A2 and A2 is greater than A1. Though this surface area is entirely different, still the electric flux, the total electric flux enclosed by them is same. So this shows that the electric flux due to a charge do not depend on the surface area and the shape of the enclosed surface around it. But one thing you need to remember is, for Gauss law, we take only the charge which is enclosed by the surface. But when we talk about the electric field, now the electric field is present inside the closed surface and also it is present outside the closed surface. So the electric field which is present inside and outside is taken, but when we talk about charge, the charge which is present inside the closed surface is alone contribute in Gauss law. Let me provide some more information about the Gauss law. From this expression, it is clear that the electric flux depends on the charge enclosed by this closed surface. The charges present outside the closed surface do not contribute to the electric flux. Then, one more thing you need to know is, the charges that are present inside this closed surface can be present anywhere. It is not necessary for them to present only at the center. So, from this it is clear that the electric flux is independent of the location of the charge inside the closed surface. Here, the closed surface which encloses the charge is referred as Gaussian surface. I have told this to you earlier. This Gaussian surface is of any shape. Well, in this case, I have drawn the Gaussian surface in the form of a sphere. It is for the reason that the charge that I have taken here is a point charge. It is spherical in shape. So if I replace this charge with something else which is not spherical in shape, then the shape of the closed surface may vary. Now I rewrite the Gauss law something like this. 5E equals to closed integral of E vector dot dA vector equals to enclosed charge divided by epsilon naught. Here epsilon naught is permittivity of free space. This is the Gauss law. Here if you look at this, it has got E vector which stands for electric field. Here this is the electric field present inside and outside the closed surface. It is the electric field due to the charges present inside and outside the Gaussian surface. Whereas this charge is the charge present inside the Gaussian surface. You remember that. And when we talk about the Gaussian surface, it do not pass through a discrete or isolated charge, but it can pass through a continuous charge system. And a very last thing I would like to tell you about the Gauss law is, Gauss law is nothing but another form of Coulomb's law, and it deals with the moving charges as well. So it is more generalized than Coulomb's law. I hope the video is useful. If you have any kind of doubt related to the topic, kindly put your question in the comment section. Thanks for watching.